Hello everybody. We are going to finish off our unit on trig and continuing on with our trig equations. So we're just going to go through a couple of different ways that we can get to the correct answer. I'm looking at these here. We've already talked about some of these. Collecting like terms, factoring, trying to get us a single trig function. For example, getting everything in terms of cosine or sine. You can divide by coefficients. You cannot, and this is really important here, cannot divide by a trig function because you don't know if it's set equal to 0. Alright, so let's just try to get on with some of these problems here. Just going to move the screen down a little bit. Alright, so everything here is in terms of cosines. I'm looking at this. It looks an awful lot like a quadratic that's set equal to 0. This is something that we can factor to solve. So we're going to go ahead and do that. This would get us 2 cosine theta and cosine theta. 1, 1. I need the O and the I of the FOIL here to be positive, so the plus is here and the minus is here. Once factored, you could set each part equal to 0. So here, 2 cosine theta would equal 1. Cosine theta is equal to 1/2. We are asked to solve on the interval. We're not looking for general solutions here. So where is cosine equal to positive 1/2? We would be looking in both quadrants 1 and 4. And that would be pi over 3 and 5 pi over 3. For the other piece here, cosine theta would be set equal to -1. Where is the x -1 on our unit circle? And that is at pi. Okay, looking at problem number 2, I've got cosines and sines. So I'm going to take out this cosine squared theta right here and replace it with 1 minus sine squared theta. So that was one of our tools to get everything in terms of one trig function. Bringing down the rest of it. Is set equal to 1. These ones on each side here will cancel out. Let's combine up our like terms here. This is also working like a quadratic. We're going to factor out a common term, which is sine theta. I'm going to bring out a negative sine theta just to kind of, I don't like starting with a negative lead here. So I'm going to take out minus sine theta, leaving me with 2 sine theta minus 1 is equal to 0. When I set minus sine theta equal to 0, even when dividing by a negative, sine theta is still 0. So this one here did not ask us to solve on the interval, so we're going to give the general solution. So first I'm going to just say to myself, where is sine theta equal to 0? That is both at 0 and pi. Those are exactly one semicircle apart from each other, so I can write this just as one term here as 0 pi plus pi k. It also could just have been written as pi k. Both of those are acceptable answers. For the second part here, sine theta is going to be equal to 1/2. So I want to know, where is sine theta equal to 1/2? That is at pi over 6 and also 5 pi over 6. They are not a half circle apart or a quarter, so we will have to just add the 2 pi k onto both of these, and there are your solutions for number 2. Alright, so let's take a look at number 3. I'm going to take out this 2 theta, and since everything on the other side is in terms of sine, I'm going to replace it with the identity 1 minus 2 sine squared theta. At the same time, I'm going to bring every item on the right side over to the left side. This way I have everything set equal to 0. 1 plus 2 would get me a total of 3, and combining up the like terms on the sine squared thetas is going to get me minus 4 sine squared theta is equal to 0. Sine squared theta then would be equal to 3 over 4. And to get rid of the sine squared into just sine, we're going to take the square root, which you do to the left, we also do to the right. Remember, when square rooting, we need both the plus and the minus answer. And we wind up with plus minus root 3 over 2. So where is sine theta equal to that? This one did ask us just to solve on the unit circle, so that would be at pi over 3, 2 pi over 3, 4 pi over 3, and finally 5 pi over 3. So those would be the 4 answers that would solve this equation for problem number 3. Okay, let's flip your papers over here. We just have 3 more problems to go. Let's scoot this down. So I'm looking at sine 2 theta. There is only one identity for sine 2 theta, so I'm going to replace that piece of it with 2 sine theta, cosine theta. This sine theta is still here. And at the same time, I'm going to subtract what's on the right over to the left so I can be set equal to 0. Both terms here share a single cosine theta, so I'm going to factor that out. And that's going to leave me with 2 sine squared theta minus 1 is equal to 0. Once you're factored, again, you set each of the factors equal to 0. So we'll just work on this piece here. Where is cosine theta equal to 0? That is at pi over 2 and 3 pi over 2. Since we're not asked to solve on just the unit circle, I'm going to give the general solution. Pi over 2 and 3 pi over 2 are exactly one semicircle apart from each other. So we're going to just write this as one single term as pi over 2 plus pi k. For the second term here, we're going to get sine squared theta is equal to 1/2. Taking the square root of both sides to get just to sine theta. Remember, plus minus. That's going to be 1 over the square root of 2. Once rationalized, we have root 2 over 2 plus minus. So this is happening in all 4 quadrants. Right here, 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 here. At pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Each one of these are exactly a quarter turn around the unit circle. So I could write this as one single term of pi over 4 plus pi over 2 k, because it's half a quarter of a turn, and that's where that pi over 2, and I don't need to list out the 4 terms. This will catch each one. From here I add pi over 2, I wind up here, pi over 2 here, pi over 2, and you just keep going around and around. Okay, so that's the way to, that only works, you only see that one on the pi over 4s. Alright, let's take a look at the last 2 problems we've got. So looking at this guy here, the first thing I'm going to do is divide through by 2. And the reason I picked 2 is because then this looks like a familiar identity to me. So that becomes 2 sine x cosine x is equal to 1/2. This is the identity for sine 2 theta is equal to 1/2. And when we have these double and triple, we're going to have a replacement here. So I'm going to let mu equal 2 theta for the moment. So the sine of mu is equal to positive 1/2. So where is that happening? Where is sine of any number positive 1/2? Our two choices are pi over 6 and also 5 pi over 6. But remember, we're not solving for mu, we're solving for 2 theta. So we're going to have to set each of these equal pi over 6 plus, and we put that general term on the end to help us get the actual solutions. I'm going to divide everything through by 2, so I get theta is equal to pi over 12 plus pi k. And if I let k equal 0, I get pi over 12. If I let k equal 1, we wind up with 13 pi over 12. If I let k equal 2, it would make more than one full rotation, so these two answers will stop here. We'll do the same thing for 5 pi over 6. So 2 theta is equal to 5 pi over 6 plus the general term to help us come up with our solutions. Dividing everything through by 2, I got 5 pi over 12 plus pi k. If I let k equal 0, we get 5 pi over 12. If I let k equal to 1, I'm going to add 12 pi over 12. That is 17 pi over 12. Still, if I let k equal 2, again, we'd go past one full rotation, so we're going to stop there. Those are the 4 solutions. All right, the last problem here, we need to talk about checking for extraneous solutions. This should only occur once you start squaring these equations in order to solve. So I'm going to take this because I can't do anything. I can't replace it. I need to get into those Pythagorean identities. So the best thing to do is go ahead and square both sides. Now remember, when squaring, you are foiling. You need to catch the O and the I terms. So we're going to wind up with sine squared x plus 2 sine x cosine x plus cosine squared x is still equal to 1, because 1 squared is 1. These two here and here, sine squared x plus cosine squared x is 1. And the ones on each side will cancel, so eventually what we're looking at is 2 sine x cosine x is equal to 0. 2 sine x cosine x is the identity for sine 2x equal to 0. As before, we're going to let mu equal to x. So where is mu equal to 0? That's going to happen at 0 pi and pi. I can write this just as one general term of 0 pi plus pi k, keeping in mind that this is equal to 2x. Now 0 times pi is just 0, so you wind up with 2x is equal to pi k, and when I divide by 2, I get x is equal to pi over 2k. So, just running out of space here, I'm going to continue over here. If I let k equal 0, that's going to get me, if I put 0 here, this whole thing will drop, so we will get 0 pi. If I let k equal 1, you're going to get pi over 2. If I let k equal 2, I'm going to get pi. And if I let k equal 3, I'm going to get 3 pi over 2. And if I let k equal 4, then I would make the full rotation. Now, since I had squared these, we need to plug them back in. So, for example, here, again, remember, original equation is sine x plus cosine x is equal to 1. If I put 0 pi in for sine x, we'll do this one here. The sine at 0 pi is 0. The cosine is 1. That equals to 1, so this guy is a check. If I put pi over 2 in for sine x, that's going to be 1. And then the cosine is 0. So this guy also checks. If I put pi in here, I get 0 for sine, but then I get -1 for cosine. So this guy here is extraneous. It doesn't work when we plug it back in. And the last one at 3 pi over 2, sine x would be -1, cosine would be 0. That also does not add to 1, making this solution extraneous as well. And the two solutions would be 0 pi and pi over 2. Alright, with that we close out our lessons on the trig. We'll be practicing, getting ready for some assessments, and then we'll start again on the next unit.